This is lesson 9.5, standard electrode potentials. So the standard hydrogen electrode is what all cell potentials, or the potential to do work, or the voltage is based on. So they're all compared to the hydrogen electrode. And the hydrogen electrode is given a cell potential of 0 volts. So a standard half cell is under standard conditions, which means the solutions are all 1 molar, the pressure is 100 kilopascals, everything is a pure substance, the temperature is 298 kelvins, and in half cells that do not contain a metal, platinum is used as the electrode. So the standard reduction potential, which has this funny symbol E0, is when the standard hydrogen electrode is connected to another standard half cell by a circuit, and from this the reduction potential is measured. It's always given for the reduction reaction, and it does not depend on the total number of electrons. The more positive your E0 value, or your cell potential, the more readily your metal is reduced. Now, we can write half cells in an abbreviated form. So if we were to write a half cell, we would write the metal anode dash the anode products, so what you're forming at the anode, 2 dashes the cathode products, or the reduction products, dash the cathode metal. For example, here we have hydrogen losing electrons to form hydrogen ions. So remember, anode is where oxidation occurs. So we have hydrogen as the anode. The products are H+. Dash dash means the other cell. And here we have copper being reduced, so we have copper ions forming copper. Now, our cell potential is always going to be equal to the cell potential of the reduction reaction minus the cell potential of the oxidation reaction. So here's an example. Calculate the electromotive force for a voltaic cell constructed from a zinc half cell and a copper half cell, and identify the anode and the cathode. So if we look at our chart of reduction potentials, we'll see that the reduction potential for zinc to be reduced to form zinc metal is negative 0.76 volts, and our reduction potential for copper is 0.34 volts. Now, whichever one has higher has the greater potential for reduction. So the copper is higher, so it's going to be reduced, and the zinc will be oxidized. So we're going to use the copper for the E red, so 0.34, minus the oxidation cell potential, negative 0.76. So overall, the cell potential for this cell is 1.10 volts. So that's what the voltmeter should read if you were to hook up these two half cells in a voltaic cell. Remembering back to topic 5 in spontaneous reactions, remember Gibbs free energy. If your cell potential is greater than 0, you're going to have a reaction that is spontaneous. So your reaction will just occur. If your cell potential is less than 0, your reaction will be non-spontaneous, meaning that it will not occur. The cell potential, however, does not give you any information about the rate. So even if it is spontaneous, you might not be able to tell it is spontaneous unless you were to observe it for a long period of time, because the rate might be so slow that you're not able to see it from the naked eye.